So during the previous classes we learned about why there are different kinds of neutrinos and how to detect them. And for a long time, sort of, that was the story of neutrinos. There is nothing more, that they exist, and okay, if you want to make an effort, this is what you should do to detect them. However, there was something which happened in 1960s, but people were not, only a very small select group of people were excited about it. Rest of the particle physics community sort of said, yeah, it's there, but however, suddenly in 1980s, neutrinos became, especially neutrino oscillations, became a hot topic of research. So first I'll give the brief history and then we'll talk about neutrino oscillations. While talking about Reno experiment, I also mentioned that there was an experiment by Ray Davis at the same reactor complex where he looked for this signal. And he didn't see any signal, whereas Reno saw a signal, and we interpret it in terms of the lepton number. Electron has lepton number +1, so I should have a neutrino rather than anti-neutrino that's being emitted by the reactors in order to drive this reaction. So Davis started looking for an intense neutrino source, and there are no intense neutrino sources on Earth, because in beta decays you have antineutrinos emitted. Okay, you can have beta plus decay where a neutrino is emitted, but number of such nuclei undergoing beta plus decays is quite small. Then a collaborator of Davis, John Bacall, who I believe was a nuclear physicist, but he was applying the techniques of nuclear physics to energy production in the sun and especially in the sun. And he pointed out that sun is a intense source of neutrinos. In fact, a billion neutrinos are passing through my fingertip every second, even as I speak to you. Of course, those neutrinos are not energetic enough to drive this reaction. This reaction has an energy threshold of 0.86 MeV. So you need a neutrino with energy greater than that to drive that reaction. Whereas most of the neutrinos from the sun, they have maximum energy of 0.4 MeV. However, there are other neutrino producing reactions in the sun, in particular what is called 8 boron decays into which nucleus does it decay into? I guess beryllium plus E plus plus mu. So, in the core surface calculations, Bacall, Prof, noted, calculated the rate for this reaction. First thing is the Q point for this reaction is something like 14.6 MeV. So, certainly a neutrino that is emitted in 8 boron decay can drive the Davis reaction. Question is, what is the flux? How much boron 8 is being produced in the sun, so that when it decays, do we get enough number of neutrinos? And according to Bacall's calculations, it was estimated that a 600-ton detector will detect So, Davis designed his detector in a place called Homestake. Built a 600-ton detector and set up the system to filter the argon atoms. And started taking data in 1964, and in 1968 the first results were announced. Good news, there were 37 argon atoms. Which means that the Ray Davis reaction was actually taking place, and the detector built by Ray Davis was detecting neutrinos from the sun. Bad news is observed rate is 1/3 predicted rate. So, this raises various questions. Question number 1, are Bacall's calculations correct? I mean, this prediction is based on Bacall's calculation of production of 8 boron in the sun. Are those calculations correct? One thing everybody agreed is the concentration of 8 boron in the sun depends on the temperature of the sun, the core temperature of the sun, to the power 10 power 24. Okay, that is Bacall's calculation. If you do it in a different way, instead of 24, maybe you get a slightly different number, but a very high power. And if I choose a value which is 5% less, then I can easily get this 1/3 suppression. So that was the attitude most people took. That what we see is the surface of the sun. What is happening inside the sun, we don't know. We have a series of educated guesses, Maybe if we reduce the core temperature of the sun by 5%, then everything matches. No need to worry about it. So this was the attitude people took until 1984. And in 1984, or I should say between 84 to 86, three things happened which made people to change their minds. But before that, let's pick up another thread of the story. I discussed in the last class that in 1962, the second neutrino experiment was performed, and they established that there is a neutrino occurring in pion decay is completely different from neutrino occurring in the beta decay. So, and both neutrinos are very, very light. In fact, in principle they could have been massless, but they are very, very light. So, three Japanese physicists in the same year, they made a proposal. They said that, okay, an interaction is producing this neutrino, but that need not be the actual eigenstate when it propagates. So they said that mu e and mu mix to form two mass eigenstates mu1 and mu2. By the way, this kind of mixing is quite well known in quantum mechanics. For example, when we solve hydrogen atom problem using Schrodinger's equation, we classify states in terms of Lm and half ms. But when we solve exactly the same problem using Dirac equation, where it is the total angular momentum that is conserved, so we now say that, okay, we shouldn't consider the states of Lm half ms, we should consider the states of Jm, which are linear combinations of the other states. So depending on what Hamiltonian you consider, states can mix. And of course, the mixing usually happens when these states have energies close to each other. If I have one state with energy E and another state with energy 10E, the rules of quantum mechanics allow mixing, but I need to have a Hamiltonian which will mix the two. And finding such Hamiltonian is actually, it's almost impossible. Whereas there can be a lot of perturbing Hamiltonians which can mix a state with energy E to a state with energy 1.1 E. So that is something similar here, but there is an important additional constraint. Let us say I have a nu E which is produced in beta decay with energy E and momentum P. And if this is an actual particle I can see in the lab, and I should assume so because I have a neutrino coming and interacting in the Cohen-Reines detector, then it should satisfy what we call on mass shell condition only if this condition is satisfied, I will actually see the particle in the lab. But if I now say that no, nu E is an admixture of two different mass eigenstates, one with mass m1 and the other with mass m2, how can I satisfy this mass shell condition? Well, here quantum mechanics comes to our rescue, because this E is not a single number. For convenience sake, we think of, in most of our calculations, we think of these particles having a definite energy and a definite momentum. But strictly speaking, we should think of them as wave packets. And when you think of a wave packet, you necessarily have a spread in E and a spread in P. So if you compute E square minus P square, I will not get a single value, I get a spread of values. So both if I have this E square minus P square, it has a range which let me call m square min m square max. And if my two values m1 and m2 fall within this range, then I can have nu1, I can think of nu1 as a non-mass shell particle and nu2 as a non-mass shell particle. And which means that this difference m2 square minus m1 square should be very small. So, for example, why don't I think of mixing between electron and muon? Logically, if I can think of mixing between nu E and nu mu, I can think of mixing between electron and muon also. They both have same charge, same spin. So, but we don't do that because the masses are very different. So, even if I think of such a mixing, the effects of that mixing, they will sort of disappear very, very fast, and for all practical purposes, I take electron to be a mass eigenstate and muon to be a mass eigenstate. But in the case of neutrinos, which even today there is no direct evidence of non-zero mass, we only have the upper limit of 1.1 electron volts. So as long as their mass differences are small, of the order of fraction of an electron volt, then this mixing is possible and we should see visible effects of this mixing. So that is the argument made by Maki, Nakagawa and Sakata in 1962. And by the way, Sankar is a very famous physicist, well respected all over the world. But for whatever reason, this idea, very few people outside Sankar's group actually knew of this idea. And but luckily, one of them is a famous neutrino physicist called Pontecorvo. And when the Ray Davis results were announced, and it was said that observed rate is 1/3 of the predicted rate, Pontecorvo, along with a younger colleague called Bianchi, made the proposal that because of this mixing, the electron neutrinos emitted by the sun are oscillating as they are traveling from sun to earth. They are oscillating into muon neutrinos, and when a muon neutrino with the energy of 10 MeV, if it interacts in the detector, it's not capable of producing a muon, so that is why there is no signal. That was the explanation given by Bianchi and Pontecorvo soon after the results of Ray Davis were announced. But there were various objections. Objection number 1 was, even if you assume what Bianchi and Pontecorvo were saying is correct, you can get a suppression of half, not 1/3. So that was first objection. And well, basically people felt this idea of neutrino oscillations was just too fancy. Anyway, there is a ready-made solution to the problem. You reduce the solar core temperature by 5% and everything matches. So for almost 20 years, people didn't pay too much attention to this solar neutrino problem. I mean, both Davis and Bacall were very well respected physicists, so every conference people would mention, yes, there is solar neutrino problem, but the likely solution is something to do with the temperature of the sun.
Why didn't they consider mixing with tau neutrino?
Yeah, well, that is certainly true, but tau neutrino was known only 10 years later, and certainly people then pointed out that if you include tau neutrino, then one can get 1/3 suppression. Certainly that was known, yeah.
So, why did they propose this theory, mixing in 1962 when solar deficit was also not found?
No, so they proposed it as a possibility. So they were
Motivation?
No, that's what. There is no data which made them make this proposal. Actually, this raises an important, there's a historical debate. This idea of mixing of two fermions to produce mass eigenstates. So, as far as we know, the first proposal was made in 1962 by these Maki, Nakagawa and Sakata. In 1963, Cabibbo made similar proposal where he talked about quark interaction eigenstates mixing to form mass eigenstates. But Cabibbo made that proposal to solve a problem. You measure the Fermi constant in muon decay and Fermi constant in beta decay. Originally, the two values were equal to each other within experimental errors, but as precision improved, the values began to differ. So much so that it was established the two numbers are different by about 2%. So, which was a bit of a shock, because people were talking about universal Fermi interaction, but the weak decay responsible for muon decay, weak interaction responsible for muon decay has 2% higher strength compared to weak interaction responsible for beta decay. And it also sounds a bit ridiculous having two interaction strengths which differ by 2%. And then there is a third issue, that is, there are so-called strange particles which are known to decay through weak interactions, and the weak interaction strength which talks about which controls strange particle decays, that's an order of magnitude different compared to the weak interaction, the Fermi coupling constant. So it looked as if there are three independent weak interaction strengths. And what Cabibbo's proposal, if you believe Cabibbo's proposal, it almost sounds trivial. It's just playing around with numbers. I have three numbers: Fermi coupling constant measured from muon decay, Fermi coupling constant measured from beta decay, and Fermi coupling constant measured from the lambda baryon decay. Three numbers. And what Cabibbo noticed is simple numerology, nothing more. But here comes the imagination. He said, I will say there is only one Fermi constant, G mu, and I write G beta as G mu cos theta and G lambda as G mu sin theta. Then obviously this equation holds, and what does this mean? This will occur. G beta will be G mu cos theta and G lambda is G mu sin theta if I assume that the quark which is interacting is actually sum of two mass eigenstates. So that was the proposal made by Cabibbo. Very imaginative proposal. But he made the proposal to solve this problem of three different weak interaction constants. And he restored the idea of universal weak interaction. Whereas in the case of Maki, Nakagawa and Sakata, they just proposed it as a possibility. There is no sort of urgent problem waiting to be solved. They said, if you have two neutrinos, both of which are very light in mass, theoretically this possibility exists. And again, by the way, if you look up this paper, I'm sure all of you know of this website called Inspire Hep. So if you look up this Maki, Nakagawa, Sakata paper, it has almost 5,000 citations. And once during lunch hour, I looked at some of the early citations. Between 1962 to 1986, roughly over a 25-year period, this paper had about 30 citations, 25 of which are from members of Sakata group. Only sort of 5 people outside Sakata group were aware of this paper. So, I mean, it's a totally off the wall idea, and in fact, the idea of using that mixing to predict neutrino oscillations, I believe that was done by Bianchi and Pontecorvo. So, how to practically see a signal for the idea of mixing, I believe that was done 6 years later by Bianchi and Pontecorvo. And to complete the story, in 1986, three things happened. One is the homestake experiment was calibrated. See, another doubt people raised about Davis's result is, okay, you are able to extract the argon atoms, fine, but I mean, are you extracting all the argon atoms that are being produced? Is the efficiency of extraction what you claim it to be? Because you are trying to extract 30 argon atoms out of 10 power 30 chlorine atoms. So, which is a valid question to ask. So, what Davis did is he had a powerful artificial source made, which undergoes beta plus decay and emits electron neutrinos. Kept it near his detector, and of course you can't turn the sun off. Cohen dryness, there is a reactor on and reactor off, but for Davis there is no sun on, sun off. But this artificial source was the flux produced by this artificial source was 10 times more intense than the flux of neutrinos from the sun. So the neutrinos from the sun were sort of 10% background in this calibration experiment, and the calibration was within what was claimed by Bacall. So there was no doubt that the observed rate is actually 1/3 of predicted rate. A second thing was Kamiokande also saw eight boron neutrinos through this reaction. Kamiokande is a water Cherenkov detector, so a high energy charge particle passing through the detector will produce a Cherenkov light. So if a 10 MeV neutrino comes and hits an electron and passes on most of its energy to it, then you have an electron coming out with an energy of some 7 or 8 MeV, and that is high enough energy for it to produce Cherenkov light, and Kamioka could detect it. Of course, there is a huge background, but they were able to suppress the background because you have the correlation with the direction of the sun. So this is my detector, and if the sun is here, and the neutrino comes and hits it, then the electron would go like that. So you look for electrons opposite to the whose momentum is opposite to the direction of the sun, and they were able to establish that if you look at 5 to 10 MeV electrons in their detector, then the direction opposite to the sun, there is an excess compared to all other directions. And in fact, some of my fellow PhD students actually worked on this problem. There was a group in our university who were members of Kamiokande experiment, and there's a man called Su Bong Kim, who is now the head of what is called the Reno Experiment. He was a couple of years junior to me, and he was the one who actually worked on this problem, establishing these solar neutrinos in the detector. And they also saw roughly 1/3 suppression. So this is actually a very important result, because you are detecting solar neutrinos using a completely different technique, and you are detecting them in real time. Davis used to collect argon atoms once a month. So, whereas here you see the neutrinos literally coming into your detector. And the suppression these people saw matched the suppression that Davis saw. So, which really said, okay, there is 1/3 suppression between prediction and observation, but that still left the question: is the prediction correct? They said this is almost 25 years later since the problem started, and during this time there was a lot of progress in a field called helioseismology. That is, the surface of the sun, it's not a perfect sphere. There are perturbations, and people were able to measure those perturbations and worked out a theory of what is happening in the sun which is causing those perturbations. And this theory required a particular temperature profile of the sun. So the possibility that temperature of the core of the sun is 5% lower, it is sort of became more and more unlikely with advances in this helioseismology. So, which meant that there indeed is a discrepancy. And the third development is actually theoretical. So, two young Russian theorists wrote a paper saying that under certain circumstances, even if the mixing between electron and muon neutrino is very small, as the neutrino is passing through the matter in the sun, because of dynamical effects, the small mixing angle can get amplified to a large mixing angle, and in fact it can lead to total conversion of all the electron neutrinos into muon neutrinos. That was the inverse, that is the result of their paper. And luckily for them, one of the most famous physicists in the world, Hans Bethe, I hope you heard the name, or pronounced, sometimes Indians pronounce as Bethe. He read that paper and he liked the idea very much, so he reworked some of those arguments and wrote another paper, and which caught the attention of essentially all the particle physicists, if not all, a large fraction of them. And after 1986, I mean, the number of papers being written on neutrino oscillations, especially on this Mikhail-Smirnov effect. So if you make a plot, you will see it like goes like that. So 1986 is somewhere here. Before that, number of people thinking of neutrino oscillations, I don't know, maybe there were 10 people in the world. But after 1986, practically everybody wrote a paper on neutrino oscillations. So it's like, I mean, a child being given a new toy and everybody wants to play with that. And not only that, so because of this huge interest in neutrino oscillations, people also started thinking about how to design neutrino oscillation experiments, and the experimental effort in neutrino oscillations really took off after that. I should mention two other important things which happened after 86. So this is after 86, but sort of related to these developments. So most of the neutrinos produced in the sun, they are due to fusion of two protons. That is the main energy producing mechanism in the sun. And those neutrinos have a maximum energy of only 0.4 MeV. So Davis's experiment couldn't see them, Kamiokande couldn't see them. Question is there a way to see them? It was found that this reaction has a threshold of only 0.25 MeV. So if I can collect enough gallium, number one, and devise a method of extracting a few atoms of germanium from that, I can observe the interaction of the proton-proton fusion neutrinos in my detector. But question is, where to get the gallium? From where will you get the gallium? And second question is, even if gallium is available, how will you buy it? Because gallium is a very important industrial element. Why is that? You've studied some bit of semiconductors. So what are the important semiconductors? Well, first germanium, silicon, and then among the others gallium arsenide. So it has a lot of strategical value. So even if you want to, somebody wanting to do particle physics experiment with 20 tons of gallium, such a person is competing against the electronics industry. And how many of you know of something called Cold War? Does the expression make any sense to you? Well, you all know about nuclear weapons and who got nuclear weapons first and who got nuclear weapons second? Russia. And already, even though they were allies during World War II, because of course there was a common enemy, but by the end of World War II, it was obvious to almost everybody that there is going to be a clash between America and Russia. In fact, Winston Churchill gave a famous speech, I think in 1946, where he used the word Iron Curtain. Said there will be an Iron Curtain between Russia and the Western Europe. And so you have these two sides which built fancier and fancier nuclear weapons, and each side tried to dominate the world. And it was a very scary situation, and I partly grew up through that during 60s and 70s, and the headlines in India were scary enough. And later, when I went to the US for PhD, I was talking to my fellow PhD students who grew up in the US during the same time. And apparently they used to have periodic drills where they would go and spend 2 hours in bomb shelters. But luckily, people on both sides realized that if they launch nuclear attack, it means the end of the world for everybody. So they refrained from launching nuclear attack. I'm telling this because this gallium experiment is one of the few cases where the two sides actively collaborated, because Soviet Union, it used to be called Soviet Union, which is Russia plus some surrounding countries. Soviet Union was the world's largest producer of gallium. So, and despite this confrontation, both sides allowed the scientists of the two sides to talk to each other on pure research matters. By the way, these scientists on both sides, they were working on bombs. In particular, two famous names, John Wheeler on the American side and Zeldovich on the Russian side. They were both heavily involved in bomb design, but they were also involved in lot of problems of pure physics, in particular black hole formation, etc., etc. And they were allowed to meet, and they used to freely talk to each other on problems related to black holes. So, because of these exchanges between scientists, a deal was made that between, I think, about 75 to 85, Soviet Union would set aside 10% of their gallium production every year to build a gallium detector, and Americans will provide the necessary additional expertise, chemistry expertise needed to sort of keep the gallium in a liquid form so that you can push it through a extraction mechanism and develop the extraction techniques, etc., etc. And the detector was built in a place called Baksan. And it's called Soviet American Gallium Experiment. Actually, by the time the detector started taking data, Soviet Union collapsed and the successor state was Russia, but of course, obviously, they didn't want to call their experiment RAGE. They kept the original name. And by this time, Europeans also woke up to the possibilities of the gallium experiment, and they built a competing experiment in Gran Sasso. This is called so these two experiments from 92 onwards, they started producing results, and they also saw suppression of solar neutrinos. And not only that, they established that the suppression of PP neutrinos is different compared to the suppression of the boron neutrinos. So boron neutrinos, we see only 1/3 of what we expect, whereas in the case of PP neutrinos, we see about 60% of what we expect. And this, in fact, is proof that this differential suppression based on energy is the proof that dynamical amplification of mixing proposed by Mikheyev and Svenov is indeed correct. We'll see those details later, but I'm just telling you the story in words. That is one important development that took place after 86, and the other important development is there were two detectors that were built around 84-85. One in the US called IMB, standing for Irvine, Michigan, Brookhaven Collaboration, and the other in Japan called Kamiokande. The name comes because it was built in a village called Kamioka. NDE stands for Neutrino Decay Experiment. I hope you've heard of this phrase, grand unified theories, which were proposed in 1974 for the first time. And they predict that proton is not a stable particle. It should decay into a positron and and a pi naught. There are other possible decay modes, but this is considered the most likely decay mode. And we are all here, we are not disappearing into thin air. So proton lifetime, it should be quite large. And in fact, there is a bound that if there is proton indeed is decaying, the lifetime should be greater than some 10 power 20 years or some such bound was already there. And these grand unified theories, based on some theoretical arguments, they predicted a proton lifetime of 10 power 29 or 10 power 30 years, some number in that range. So, and the idea was so popular that people built these two experiments to search for proton decay. And in fact, the KGF experiment, which was running at Kolar, they also modified their detector to look for proton decay. And as I told, the main signal they were looking for, and this pi naught will decay into 2 gammas. So I have a detector like this, and a proton here decays. So there is a positron and pi naught, but it gives 2 gammas. Now, proton has a mass of about 940 MeV. So, and pi naught mass is 140 MeV, it is small enough. So roughly E plus and pi naught have equal energies, about 460 or so MeV. And a 460 MeV positron, it will emit a high energy gamma ray, and that high energy gamma ray will pair produce and ... So I get a shower of particles. And this pi naught with energy of about 470 MeV, it will decay into 2 photons of energy about 230 MeV each. They will pair produce, and here also I will get a shower of particles. So the signal they were looking for is sort of one shower of particles this way and another shower in the opposite direction, and each shower should have total energy of about 460-470 MeV. Now, proton may decay, may not decay, but cosmic rays are coming from above and they are interacting with atmosphere, and that interaction was producing muons. First, they're producing pions, and pions decay to produce muons, and in all these decays there are neutrinos being produced. To avoid the cosmic ray muons, these experiments are set 1 kilometer underground so that you cut out the cosmic ray muons, but you can't stop the neutrinos. So neutrino is coming, and these detectors necessarily have to be very big because you are trying to detect a very, very rare decay. So better to have as big a detector as possible. And when you have a big detector, even if neutrino interaction is very weak, it will interact and produce a particle. In particular, I can have a nu E, and neutrinos can come from any direction, even come from below also. Neutrino produced at the opposite end of the earth, it travels through the whole of earth and comes from below the detector. and it can interact. If it is a nu E, it can interact and produce a electron. An electron of energy some 500 MeV. And this detector cannot make a distinction between a 500 MeV electron and 500 MeV positron, because the interactions that take place, they don't care about the charge. That positron will annihilate and produce with an electron only when its energy is like 1 or 2 MeV. When its energy is 500 MeV, it is more likely to emit a high energy photon. So, all these neutrinos form a background. And of course, you can also have muon neutrinos and they produce muons. That is also possible. So, the neutrino interactions in the detector, they form a background, and first thing that these experiments did is to do a thorough study of neutrino interactions in their detector. And in doing so, they made a discovery. They found so given the detector, I can define a vertical direction, and given the vertical direction, I can define a horizontal plane. Forget the horizontal plane. I can define a vertical direction, and I look at the produced muon momentum, the cos theta of the angle between the produced muon momentum and the vertical direction, and based on which I can define, I look at the cos theta of that angle. If it is positive, I call it upward going. If it is negative, I call it downward going. And when they looked at the muons produced in their detector as a function of this cos theta, they found that the number of upgoing muons is less than number of downgoing muons. Whereas in the case of electrons, the statement was not so clear. And whereas we assume that the cosmic ray flux is isotropic, if the cosmic ray flux is isotropic, we expect the same number of particles in all directions. One big problem in interpreting this result is the uncertainty in the cosmic ray flux, which is about, at that time it was about 25%. So they did various other things to overcome that problem, but they established that there is a deficit of neutrinos, there is a deficit of observed neutrinos, especially deficit of observed upgoing neutrinos in atmosphere. So that led to atmospheric neutrino problem. And so already people were playing around. So this is when neutrino oscillations became a hot research topic. So people said, you have a deficit of neutrinos, well, apply the idea of neutrino oscillations to it and see where it leads us. So the net conclusion is that
so again there, due to dynamical effect of
no, The details we'll discuss, of course, in due course, but let me give the punchline to the story told so far. First, so between 1962 to, I would say, 2001, there is solar neutrino deficit was established in various different experiments, and solution is mu e oscillating into mu mu slash mu tau with dynamical modification, or let me use the more standard word, with matter modification of oscillations and from 1986 to, well, even now, atmospheric neutrino deficit and here the favored explanation is nu nu to nu tau, and here the no evidence yet on matter modification. Mean the data that we have, you can assume vacuum oscillations and fit it, you get a reasonably good fit, and you assume matter modifications and fit it, then also you get reasonably good fit. Mean that way, Super Kamiokande experiment has the best data, and the matter modified oscillations provide a slightly better fit compared to vacuum oscillations, but that preference is so slight that it's not statistically significant. So in that sense, the jury is still out as far as these oscillations are concerned, but we have the formalism of neutrino oscillations, and that formalism fits both solar neutrino data as well as atmospheric neutrino data very well. And people have considered alternative hypotheses. For example, they considered what is called neutrino decay. Neutrino is a light particle, but neutrino oscillations require it to be massive. So imagine this light particle decaying into even lighter particles. That is more or less ruled out. And then there's this concept of decoherence. We will see what it means when I discussed neutrino oscillations, where I assume that these two wave packets, the nu1 wave packet and nu2 wave packet, they move essentially together with complete overlap. But obviously, when I have two overlaps, two wave packets, a complete overlap is a rather strong assumption. Eventually, we expect the two wave packets to drift apart. That is what is technically called decoherence. And people tried out decoherence, that also is ruled out. And various other ideas, none of which fit the data. In fact, most of the other ideas are sort of ruled out with great confidence level. And the only hypothesis which fits the data well is neutrino oscillations. In the case of solar neutrinos with matter effects, in the case of atmospheric neutrinos, the jury is still out. But we are reasonably sure, I shouldn't say reasonably, we are very sure that both solar neutrino deficit and atmospheric neutrino deficit are due to neutrino oscillations. There are discrepancies, but the main effect is neutrino oscillations. So to explain the discrepancy, you need to modify the picture, but that will be a perturbation. The main effect is the neutrino oscillation. One problem both with solar neutrino deficit and with atmospheric neutrino deficit is you don't have a control over the source. The source which is producing the neutrinos, you have no control. And also you cannot directly observe the source, so there is a large uncertainty in the flux prediction in both cases, which limits our ability to make precision measurements. So people started proposals of neutrino oscillation experiments with man-made sources where you have a control over the source. And as I mentioned in the last class, man-made sources, there are only two: reactors and accelerators. So I will stop now. In the next class, I will discuss first neutrino oscillations, the basic formalism, neutrino oscillations in vacuum, and I will discuss neutrino oscillations in vacuum for 2 flavors and then for 3 flavors, and then I will discuss the measurements made with man-made sources, and then we will go on to matter effects.
Sir,
Yeah.
is there any kind of possibility that more than 3 neutrinos may occur?
Okay. As I mentioned in the last class, we know that there are only 3 light active neutrinos. We have experimental evidence for that. So if you want a 4th neutrino, if it is light, then it should not have any known weak interaction, or if you want it to have known weak interactions, then it should be heavy. And in particular, we don't have a really compelling theory for neutrino masses. The most popular model goes under the name Seesaw Model, and in fact, Seesaw Model is a generic name. There are sort of dozens of Seesaw models which differ from each other in detail. The Seesaw model assumes that there is actually a heavy sterile neutrino, and its only purpose in life is to provide a light mass to the light neutrino. So at the end of the course I will briefly discuss that. That is from theory point of view. From experiment of point of view, I mentioned that we have this picture of 3 flavor oscillations. So once I have a definite theory, theory makes definite predictions. A definite theory makes definite predictions. But there are experimental results which do not quite agree with these definite predictions. So, but the discrepancy is, it's some, you can call it 3 sigma, 4 sigma, whatever. So it is not so compelling that we should all take it very seriously, but you can't totally ignore it either. And there are a lot of people who take the discrepancy seriously and try to explain it by assuming that there is a light sterile neutrino. But light sterile neutrino means then you have another definite theory which is again making definite predictions, and not all of those predictions are true. So there is sort of, you can even say that there is some tension between all the data. So different pieces of data seem to be pulling in different directions, and we don't have a theory which can explain these two, the pulls in the different directions. But see, these small deviations, if we sort of look back in at least in the history of particle physics, in 90% of the cases these small deviations went away, but in 10% of the cases it was an actual signal, and because the experiment is not sensitive enough, it showed up as a small deviation. And when you designed a better experiment, the signal actually showed up. So that is why people are not ignoring these discrepancies. They are thinking of how to do a better experiment to check whether it is actually there or it will go away. Okay, so we'll meet on Wednesday.